So this chapter is going to be about friction. So in this chapter we will discuss one of the type of friction which is called dry friction in section 8.1, and in the next section we will talk about some of the examples to really understand the concept of dry friction. Okay, now what is friction? A friction is defined as force resisting the relative motion of solid surfaces or fluid layers or any other material elements which are sliding against each other. So basically what friction is, that when you have two surfaces, that surfaces slide against each other, so you will face the resistance between these two surfaces. So it means that it would not be very easy to slide one surface onto another. You will face some resistive force, and that resistive force is called force of friction. Now there are many type of friction depending upon which sliding surfaces you are using. So in this chapter we're gonna explore one type which is called dry friction. It is also called Coulomb friction because it was investigated by French physicist Coulomb. So a dry friction is defined as a force that opposes the relative lateral motion of two solid surfaces in contact when there is no lubrication. So basically dry friction is a friction of resistance between two solid surfaces. So the condition is that it has to be two solid surfaces, and when two solid surfaces slide against each other, you will face a resistive force, and it would not be very easy to slide these two surfaces. You will have slight or major force of resistance, and that force of resistance which will hinder the movement of these solid surfaces is called dry friction. Now, in order to understand this concept of dry friction, let's just think of two solid surfaces. One solid surface is this one and another solid surface is this one, and we want to investigate the dry friction, that how these dry friction originated and how we can quantify these dry friction. So imagine this is a solid rigid body, and this rigid body has some weight W, and that weight acts on the center of gravity of that rigid body, and we're going to explore the center of gravity and centroid in the coming lectures. But for the sake of this chapter, we can think that this weight will act on the center of gravity, and let's just assume that this is our center of gravity point. So whatever the weight of this rigid body is, that weight is gonna act on the center of gravity. And since we wanna slide these two surfaces with each other, so we have to apply a force, and let's just say this applied force, this action force is called P, and this force is pulling the weight on that surface. So as a result of this pull, you will face resistance between these two surfaces, and this is a sliding surface. Now if you imagine, because these P and W are action forces, and as a result of these action forces you will have reaction forces. So this is weight W, and this weight W will result in a distributed reaction force on the upward direction, because we are assuming that this object is in equilibrium. So in order to satisfy the condition of equilibrium, the action force, which is W, should be equal to the reaction force, which is the delta N. This is the normal force which is acting to resist the weight. Now we know that if we apply lateral load, it will also resist that lateral load because of the thing which we discussed called friction. So there is a resistive force which is acting on the opposite direction to the weight, to the load applied, and this force delta Fn is called friction force. And since these two solid surfaces are sliding with each other and these two surfaces are solid, so this type of friction would be called as dry friction. Now, maybe you are imagining that how these dry friction or these frictional forces are originating. So in order to really understand, we need to go into the microscopic level. So if you really look into the sliding surface, so this sliding surface is actually not a plane. It has irregularities. So the surface is also not uniform. It has some microscopic irregularities, and the rigid surface is also not uniform. So because of these irregularities, you don't have the reaction force exactly vertical. So the reaction force would be somewhat at an inclined angle. So you have weight applied on it, and because of this weight you will have a reaction force, and that reaction force would not be strictly vertical because you have irregularities. So remember, in the last chapters also we discussed, when you have a horizontal plane you have a different force, and when the plane is at an inclined angle and you are applying weight, so you will have different reaction forces, or the components are also different. So considering this, you will also have the reaction forces which are at an inclined, and if you resolve these reaction forces into two components, so these two components comes out to be this normal force and this force of friction. So force of friction is just coming out because of these irregularities, and you have these irregularities between two solid surfaces, and these irregularities interlock these two surfaces. Okay, now coming back again here, if you look at it, so since this is the normal force, and this normal force is somewhat have a different magnitudes at different places, so if you try to find the resultant, you will find the resultant somewhere here. And how we find resultant somewhere here, this is also something we're gonna go deeper into next chapters, where we'll study center of gravity, center of mass, or centroid, and these kind of things. So for now you can think that this is a point where the reaction force is being applied, and one of the reaction forces N, another reaction force is F, which is force of friction. So you have two action forces W and P, and you have two reaction forces F and N, and the weight is acting at a center of gravity, and the load is acting at the centroid of area of all the distribution delta N. So that's how you determine the free body diagram of dry friction. And why this is important is because later we want to quantify this dry friction. So it's very important to quantify. In order to quantify, it's very important to understand the free body diagram of how the action and reaction forces are being established in case of frictional surfaces. Okay, so before going into numerical examples, let us just try to understand how these frictional forces varies. So we have already established that if the body is in equilibrium, then action forces and reaction forces are equal in magnitude but opposite in direction. So if we look at this figure, we have a load on x-axis, which is the action force, that is a force of push we are applying on this solid surface. So this is one solid surface, this is another solid surface, and we will apply an action force, and as a result of this action force you will have a reactive frictional resistance force. The more action we will apply, the more reaction we will receive, but there is a limit to the reactive forces, and that's what we're going to determine in this slide. So this is an applied load which we are applying on a rigid body, and this vertical axis represents the frictional force. Now if we keep on increasing the intensity of the load, so if we keep on increasing the intensity of the load, the frictional force will also increase, considering that this rigid body is in equilibrium and action should be equal to the reaction. But there comes a point where, and that point is somewhere here, so you keep on applying the load, so there comes a point, that point is referred to as Fs, and after that point this interlocking is no more capable of resisting that applied load, so the rigid body will start moving if I will apply more load than this limiting load. So you have 2-3 components of this graph. So after this load, this object or this rigid body will be in motion, but before that load this rigid body can resist that load and there would be no motion. Okay, so what is this F? This F is actually static frictional force if equilibrium is maintained. And when equilibrium is maintained, when action forces are equal to reaction forces. Now, this Fs is actually this limiting static frictional force. Now, what do I mean by limiting static frictional force? It means that at that load, or the load which is being applied, which is load P, at that load or less than that load, there would be no motion in a rigid body. But if you apply load more than the limiting static frictional force, then this rigid body will start moving. So basically, it's the maximum resistive force that a rigid body can maintain without being in motion. Now, if you have load more than this limiting static frictional force, then this frictional force would be called kinetic frictional force, and at that applied load, the rigid body would be in motion. So why this is important is because you can see if you keep on applying the load, you will have increase in the frictional force, but at the point you have maximum limiting static frictional force, your frictional resistance will decrease. So it has some implication. For example, what does that mean is that when you're applying a load on a rigid body, then if it's in static position, in order to move that load, you need a higher applied load. But once the object is in motion, you don't need that much amount of load. So in order to keep the object moving, you need a higher applied load. But that's how you calculate the static frictional forces. And in this slide, we have determined there are two types of frictional forces. If an object is at rest, then this is limiting static frictional force for a maximum load. And if an object is in motion, you have kinetic frictional force. Now, there are some characteristics of this dry friction, and we're gonna go roughly and then we'll move towards doing an example. And in example, it will become clear how we can calculate this frictional force and how we can calculate if the object will move or it will stay, or what is the maximum applied load we can apply such that under this load there would be no movement. Okay, so characteristics of a dry friction. The frictional force acts tangent to the contacting surfaces, and we have already established that this is one surface and this was another surface, and there was a load, you were also applying a horizontal load. So the frictional force was actually tangent to the contacting surface. And the maximum static frictional force is independent of the area of contact. And now this is very interesting because if you increase the area of contact and then apply a load, or the area of contact is smaller and then you apply a load, it does not impact the frictional force. And this is interesting because someone would imagine that if you have a larger contact area, then it would be difficult to move that object, but that's not the case. The maximum static frictional force is generally greater than the kinetic frictional force. And we have already seen when we were discussing this figure, this is the maximum static frictional force and this is the maximum kinetic frictional force. And we can see that the maximum static frictional force is generally greater than the kinetic frictional force. Now, at a slipping point, this is a slipping point. The maximum static frictional force is proportional to normal force. So at this point, you can calculate the maximum static frictional force by using this formula. And it says that it is directly proportional to the normal force. So higher the normal force, the higher the static frictional force. And the normal force will be higher when the weight would be higher, because normal force is directly equal to the weight of that rigid body. So frictional force depends on the weight. The higher the weight, the more difficult it would be to move that rigid body, but it does not depend on the area. If you have a wider area, it won't have an impact. After slipping, once the rigid body starts moving, the kinetic frictional force is also directly proportional to the normal force, but the constant is mu k. So this is how you calculate a frictional force when the rigid body is moving. Okay, now let us do one example, and with the help of example, it will become more clear that how this all works. So this is a crate, this is a rigid body, and this is also a rigid body, and we are applying a load of 80 Newton. And what we have to find is that we need to find that if this system is in equilibrium and the mass of this rigid body is 20 kg. So what we are interested in is that if we apply a load of 80 Newton on an angle, on an inclined angle of 30 degree, so we are interested that would this system would be in equilibrium or not. What I mean is that will this rigid body move or will this rigid body stays static? So if this rigid body is staying static after applying the load, then we can say that this system is in equilibrium. So the first step, as always, is to draw a free body diagram. So let's just try to draw a free body diagram. So this is an object and this is the sliding surface, and we already know the action force, which is load P acting at a 30 degree from a horizontal axis, and this load is 80 Newton. And we also have a weight which will act on the center of gravity. So that weight is also an action force, and that weight is equal to mg, and we know the mass, so we can calculate the weight. Now as a result of this weights and loading condition, we will have a reaction force, and that reaction force is N. And we'll also have a resistance which is called a resistive force. Now as we discussed, this would be at some angle x because of those irregularities and because of the differences between the center of gravity and the distribution of the normal force. We'll have a reaction force at some distance, and that is also because we have to cancel out the moments as well, so we need to have it at some distance. So now we have a free body diagram. This is free body diagram, and once we have the free body diagram, we can then move to use the equilibrium equation and try to calculate all these forces, because now there are a lot of forces which are unknown. So let's just first calculate the weight. So weight would be equal to mass into g. What is mass? Mass is 20 kg, and what is g? 9.81. So mass is kg, and unit of g is meter per second square. So kg meter per second square is Newton. So you will get weight equal to 196.2 Newton. So the weight is 196.2 Newton. So let us use a equilibrium of equations. So the first equation is summation of forces on x is equal to 0. So all the forces which are acting on x-axis, we will consider this here. So there are two components of this load. One component is acting down, another component is acting horizontally. So this is this is theta 30 degrees, so this would be cos, and this would be sine. Okay, so since it's a horizontal load, and that horizontal load is acting downward, so minus 80 and cos of 30 degrees minus which other force? We have force F is equal to 0. So if you do the calculation, you will get force is equal to 69.3 Newton. So that's the frictional force or the resistive force that is acting as a result of this applied load. Now let's just try to find this normal force. So for that we have to do all the forces acting on y direction is equal to 0. So how many forces are acting on a vertical direction? One is the component of this action force P, which is sine 30 degree, and then you have normal force, and then you have weight, which is 196.2. so if you do the math, you will get a normal force is equal to 236.2 Newton. So this is the normal force. Now which force is remaining? Now we have to find this x, and we also have one more equilibrium equation, that is equation of moment at O. So let's just call this point as O, because we need some reference distance from where we are calculating the moments. So this is a point O, this one. Okay, so if you use this equation, you will get a t sine of 30 degree. This is the force, and since this force is vertical force, so it would be somewhere acting here, and the distance between these two forces is, this is 0.4 and 0.4, so it would be 0.4. And the next force is the horizontal component, which is cos of 30 degree, and the distance of horizontal component from this point O is 0.2. Now we have normal force NC, and this is acting also anti-clockwise, so it should be positive, n of x is equal to 0. So if you do the math here, you will get x is equal to minus 9.08 millimeter. So what does that mean? It's coming to be negative. It means the direction which we chose was actually not correct. It's the opposite. So the actual forces, if we draw an actual free body diagram, this is the way it being acted at center of gravity. This is the center point. So we were assuming that the x is somewhere here, but the x is not here. Actually x is here. So you have a normal force acting here and the frictional force here. So that's the actual situation, but it doesn't matter. We can just initially assume any direction or position, and when we have negative result, we can change the direction and we can get the actual result of the direction. So now we have normal force also, frictional force also, and we know at which distance from the center of gravity, or from the central point which we indicated at point O, how far this normal force is being acted. Now we were interested in calculating that if this whole system is in equilibrium or not. So for that we can use the equilibrium equation, which is f of max is equal to mu s n c. So this is the maximum force which can be resisted by this system, and we have already established that. So this is the maximum force. If you will apply force more than this, then the object or this rigid body will start moving. So this is the maximum force. So if the applied load, or if our resistance is greater than this maximum force, then the system is not in equilibrium. So let's check this. Okay, so our constant is 0.3. We are given this, and it depends on the surface of these rigid bodies. And what is the normal force? Normal force is 236.2, which we calculated here, and if you do the math, you will get 70.9 Newton. So this is the maximum load a system can take without moving, and this is our it's 70. So let me write it here. Actually, f of max is equal to 70.9 Newton. So this is the maximum resistance a system can take. And how much frictional force we are getting? We are getting frictional force 69.3. It means that the applied load of 80 Newton is giving us a frictional force of 69.3, which is less than the maximum force. So we can safely say that the system is in equilibrium, but it's very close. So a little more applied load will make the system start moving. So this is chapter 8, and see you in the next chapter.